So you're all teachers, right? And what is your background? Which disciplines are you in? Textile engineering. What about you? Okay, she's not a teacher. Are you a teacher? Oh, okay, sorry. Mechanical. Electronics. Okay, so there are some people from electrical, chemistry, chemical, mechanical. Okay, so at least there are 4. So this will make more sense to electrical and electronics engineers, but nevertheless, others also will carry something with them, I think. Alright, so I'm going to talk about the use of circuit simulation in teaching electronics and power electronics. And with data center, I have a project which was to develop an app, a mobile app, based on simulation. Okay, so I'll come to that later. But to begin with, I just want to sort of go through the need for this kind of approach. Okay? And you are also free to interact, add your comments as we go along. Okay, so first let me just talk in general about engineering education in India and why everything is not perfect, why there is the need for improvement, and that will bring me to why we can use simulation, how we can use simulation effectively in engineering college teaching. Alright, so in my opinion, an effective engineering course should have the following components. One is it has to emphasize on the basics. Okay, I've gone to several colleges and students want to know about 4G, 5G, whatever, 6G if there is 6G, 10G if there is 10G, but they don't know about Fourier transform. So this is a big problem, and it's not a trivial issue, right? Unless you know basics, this 4G, 5G didn't really happen all of a sudden, right? There is 40, 50 years of experience, a lot of innovation, a lot of engineers, scientists contributing to it, and then we have 4G and 5G. So you can't just say I want to know about 5G and I'm the master of everything. It's not possible. So we have to emphasize the basics in our engineering education, which we don't, I think. And we also need to encourage students to do analytical thinking. And I'll give you an example of what happens when somebody comes for an MTech interview here or a PhD interview. And you will see what I mean by this. Enhancement of problem solving skills. So in our colleges we teach about many things, including Fourier transform, Thevenin's theorem, chemical engineering, whatever you have, thermodynamics and so on. But you ask them to solve a simple problem, unless they have looked at it before, that same problem earlier, they are not able to do it. Okay, this is the tragedy of our engineering education, and you will all agree with that. And it's not enough to just learn theory. Whenever there is a theory, if you can actually show that the theory makes sense, you can show some experiments, that always reinforces the understanding of the student. And very often the teacher just enters the class and starts delivering lecture, right? And many of you probably do that. But it is always good to point out why we want to learn about this. Okay, Fourier transform. Where does it fit in the larger picture? Why are we even interested in this? No, why don't we study something else, right? So this aspect is also often missing in our engineering education. Alright, so as I said, currently our education system does not meet all these objectives adequately, but it is not impossible. I'm fully convinced that with some effort it is possible to improve. It's possible to incorporate all of these in our basic curriculum. There are factors which are outside of our control, but if we are all determined, we can probably change that also. Alright, so here is an example. Okay, I'll just tell you. This is a real life story, right? I'm not making it up for the sake of this talk. So an MTech interview candidate comes to IIT and he is asked a question. What is the question? Plot the diode IV characteristics, a relationship for a diode. Simple enough. And even the chemical and chemistry and everybody would probably know what a diode looks like. But the electrical engineering electronics engineering students should definitely be able to draw this. Okay, so here is what they draw. Okay, it's partly correct, but only partly correct, right? So, can you tell me what is wrong with this figure? Axes are missing. Okay, that any engineer can tell, right? Now you don't even need to be electrical or electronics engineer. So axes are not even marked. What is x-axis? What is it? And they just reproduce something from memory, and this is what it. Okay, what else? Knee voltage. Okay, so there are some features of a diode IV curve here, but it's definitely not what a real diode looks like. Any other? Is there anything wrong with this part? Anyone knows? What is the breakdown voltage of a diode? Normally, axis. There are no labels on the axis. There is no tick marks on the axis. A lot of things are wrong. Okay, but this is what they do. Yeah, right. So this, it doesn't make sense without the axis, but there is. Okay, so normally what textbooks show is that they plot this in milliamperes and they plot this in nanoamperes or microamperes, and then this sort of looks reasonable. And then this axis is also different. Okay, if this is 0.7 volts, then this would be 5 volts, 10 volts, and so on. Okay, but the students have forgotten all of that, and this is what they draw. It doesn't make any sense, right? So now, if you want to draw things on the same scale, I mean, by that I mean this scale and this scale the same, this scale and this scale the same, then this is what it would look like. It's more realistic. So this is 0. The diode would conduct at about 0.7 volts if it's a silicon diode. You have to mark the I and V. You can mark it here, you can mark it here. What is I, in what units, what is V, and what is the breakdown voltage. So breakdown voltage could be 5 volts, could be 10 volts, could be 1000 volts, but it has to be marked, right? So this is what one would expect from an engineering student who has gone through the BTech curriculum. It does not happen. And it's partly because of the textbooks that we use, the way we teach. In the textbooks, like I said, this scale is in milliamps, this scale is in microamps. The student has forgotten all of that, right? And this is what he draws. Okay, it's total nonsense. Right? It's not what a diode looks like. Alright, so why does this happen? Rote learning. Our whole approach is rote learning. Okay, and this is not true only about electrical engineering. It's also true about science. It's also true about other branches of engineering. Learning without questioning. The teacher just enters the class, just goes on talking, and then the students are just supposed to listen if they're not looking at their mobiles, right? Okay, so this is something that we have to change. We should change all over. Okay, I'll give you another example. I have conducted a few workshops in several colleges, and these workshops are attended by teachers and sometimes by senior students or even junior students. So here is a question that I ask. Okay, draw what is the circuit? A common emitter amplifier, and that's the equivalent circuit. So then I ask in the class, find the bias point, or give some values and so on. So this they are able to do. Okay, so then draw the small signal AC circuit, this one. So this very often people are not able to do, right? And why, I don't know. What is meant by small signal? These people do not know at all. What exactly is small signal? What signal is small? Is it 5 millivolts? Is it 25 millivolts? If it's 5 millivolts, why is it called small signal? And what exactly should look at? Nobody knows. Okay, it's because it's not taught. It's not emphasized. Calculate the gain. Very often people don't know that. What is the point of studying an amplifier for which you don't know the gain? Right? Totally useless. So that is where we are. Here's another question. It's a half-wave diode rectifier, and this is the input voltage, that is the output voltage, and this is the input. This is the voltage across the diode. Okay, so there's a reverse voltage here and so on. And these are diode currents. So the diode conducts in this area. Then the rest of the time the current is 0 and so on. And this is the capacitor current. Alright, so now first of all, these plots nobody has seen before, although they are so very important. Nobody has seen these plots. Okay, because they are not in the textbook, nobody has seen. Tragedy. So let's say I ask some questions. What is the value of C for a repole voltage of 1 volt? Fine. Okay, they know the formula. They plug it in. They get the answer. Fine. Find the peak diode current. Some participants. Again, they do it because there is a formula for it. Okay. Starting from scratch, nobody would be able to do it. Derive the formula that you used in this part. Nobody. Not a single person. Okay. Sketch the diode current waveform. Not a single person. Okay. So they don't know what this looks like because they have never seen it. What is the use of calculating this peak diode current when you don't know what it looks like, right? Alright, so this is just a background, right? I'm just first pointing out the problem, and I'm going to talk about the challenges. The challenges are many. It is not just from the academic side. There are other challenges as well. First of all, our problem, the biggest challenge is with the workforce. Our very often the teachers enter colleges, I mean in the teaching profession with very limited experience. I know colleges where fresh BTechs or BEs are given a contact position and they are asked to teach. What are they going to teach? They have limited experience. Then there is attrition, right? So this guy who has come, guy or lady who has come after fresh BE or BTech on a contract position with some salary. Sometimes they don't even get salary on time. I know this. What is he going to do after 2-3 years? He gets an IT job, he goes, right? Done. Now, all his experience, whatever he has learned in the past, 2-3 years, is gone. So that is because there's, of course, everybody seeks greener pastures, and we don't blame them on that. The other big problem is that they themselves have not had exposure to good teaching methods. Okay, they have never seen the diode plots the diode current plots that I have shown. So how are they expected to pass that on to their students? So that is the problem. So that is the problem with the workforce. Students, they have low motivation very often. Sometimes they also have low competence depending on the college, but this is not always true. Wherever I have gone, I have always seen that there is a 10-20% students who are pretty bright. It's just that they are not exposed to proper teaching. Okay, and therefore they are capped by that limitation. Okay, their abilities, their performance is capped because of good teaching or even textbooks. And of course, the students will always say, "ये सब करने के बाद क्या है?" Also, after all that, they will take up a job. Many of them will take up an IT job or join a bank or some analytics and so on. Why should I do all this electronics or diode current, this capacitor, this, that, right? So is this stuff really useful? So that is a question the students ask. I have no answer for that, but hopefully if our country evolves and we become electronics manufacturing, or if we create enough jobs in which these subjects are actually used, then this situation will change. Evaluation. Very often many colleges, they are from Mumbai University or some university and so on. The exams are set by some external agency. There is no communication between the teacher who teaches the course and the person who sets the paper. There is absolutely no communication, and there is no effort for any communication. Okay, so then therefore what you teach in class is the student is always going to ask, why should I learn what you are teaching, right? I mean, the exam is going to come from somewhere else. Somebody else is going to set the exam, and if I learn what you are teaching, can I score marks? If I cannot score marks, why are you forcing me to do all this, right? So that is the big problem, and this problem is not there in autonomous. Are any of you in autonomous colleges?
Yeah.
Which college?
UP Textile Technology Institute.
Okay, so okay, Punjab University is autonomous. So in autonomous colleges, at least you have the advantage of setting your own papers. So the teacher teaches whatever in class, and then he or she can ask questions based on that material, and therefore the students are more or less obliged to learn all that material properly, and they know that okay, if I learn this, there is something for me, right, at the end. Then there is this another big problem in many private colleges. There is pressure from the management. So the result has to be good, right? Result. So result is all important. Nothing else is important, right? Because if the result is not good, they're not going to get more students next year. Okay, so that result is the driving force, and so therefore, what is the problem with this? So you cannot ask any questions which are even slightly difficult, right? Because then the number of students failing might increase, might grow rapidly. That is not allowed. So that is the problem. Social issues, right? So apart from all of these are like technical slash academic issues, there are social issues. There are other attractive career choices for students. So why should I bother about core, right? Core areas. Okay. And so this is finally, as I said earlier, this really boils down to this question. So are there enough jobs for engineers? Suppose the students really work hard, the teachers work hard, they learn the subject matter very well, they emphasize on basics, analytics, everything. At the end, are there enough jobs for engineers? I think the answer right now is no. But I hope that this situation will change in some time. Alright, but we will leave all that apart and we will just sort of focus on what is it that we can do. Now my take on all this is, there are problems, but this should not be used as an excuse not to teach well. Okay, and I'll tell you why. So you heard of IIT students doing very well, right? Most of you. Many of our students have gone forward. They have started their own companies. They have sold their companies for very big sums. They have donated money to IIT, etc., etc. Right? So many of them are very, very successful, and in fact examples to emulate by others. And now, why did that happen? That did not happen because they are staying in their core areas. Maybe they also moved to even banking sector or financial sector. Okay? But they have gone through a very rigorous training process here in all subjects. Whatever subject they studied here, whether it is electrical engineering, electronics engineering, chemical engineering, chemistry, maths, whatever, it was done with some rigor. It was done, and the student was convinced that okay, there is a method about everything. Okay, now that method he has gone and applied to finance maybe, or maybe something else. But that basic method that he learned here stayed with him. Okay, so that is why, in spite of all of this, we should try our best to teach well and then convince the students that all that we are doing is logical and it makes sense, right? Which often does not happen. Okay, so what is it that we can do about courses like basic electronics? So what are the effective techniques that we can use? We can clarify concepts through numerical examples in class. So you cover a topic, for example, phasors. Give a problem in class, ask them to work it out, right? Some of them will not be able to do it, but then they will work it out still with your help and they'll still learn. If you don't do that, they just go home with some formulas and not even correct formulas. This is another very powerful thing, and that is actually what is going to bring me back to this simulation theme. Illustrate new ideas with simulation results, animation, etc. in class. Okay, so you're teaching, let's say, some 555 timer. At least all the EE people have heard of 555 timer, and you know what the waveforms look like. So you simulate that circuit and show the waveforms in class. Okay, that stays in mind much better than just drawing it on board or just describing it in words. Assign homework problems. Assign lab project, for example. Electronics, this is very easy to do because you don't really need very massive equipment or expensive equipment, and you can easily assign a lab project which is in a course like electronics, which is of duration, let's say 6 weeks. So you give them 6 weeks, ask them to make a digital clock. There is no digital clock here. Okay, it's simple enough circuit and interesting enough. Okay, you can and that really drives them. I mean, definitely at least half of the class will enjoy doing that. There are lots of resources, and this is definitely not an excuse that there is lack of resources. For example, I have my own slides as well. There is also a MOOC on electronics, and this is what I've been using, my own public domain circuit simulator. It's called Sequel, and this app that I'm going to describe is basically it uses this simulator. And there are lots and lots of resources from the internet, video tutorials, data sheets, whatever. So this resources is never a problem in teaching well. In the olden days, there used to be textbooks which were by foreign authors, and the editions were foreign editions. Okay, so they used to cost a bomb, like $60, $70, right? And when you purchase it in India, definitely it used to pinch. So as students, what we have done is we have bought textbooks from the graduating seniors. So they would pass it to you at a discounted rate. you pass it on to the next student at a discounted rate. All that is not required anymore because it's just so much on the net, and all of the foreign books are now available in Indian editions. Those who want to read a book, money is not a constraint anymore. Alright, so textbooks. So now there are very good textbooks available in Indian editions, and many of our students also know how to get these as PDF format. Sometimes legal, sometimes not legal, but they know how to do it, right? But this textbooks is a very important matter, and I want to explain why. Sometimes we end up using bad textbooks, and it hurts. It hurts the students. So the textbooks, if you use one, have to be selected very, very carefully. Not just any arbitrary book will do. Here is an example. Okay, this is an Indian textbook. Right? Okay, there are 4 or 5 people in electrical engineering, right? What is this? Okay, this says here what it is. Amplitude modulation. Can you tell me what are the problems with this? There are lots of problems with this figure. So can you tell me what the problems are? And this is what the students see, right? And this stays in their mind. Tragedy. So what are the problems? Normally when you teach, what is the carrier signal? Sinusoid? Is it looking like a sinusoid? I don't know what it is looking like. It's definitely not looking like a sinusoid. Right? Why this has happened? Because this author has given the whole project he has drawn it on paper and he's given it to a draftsman, and the draftsman has applied his own imagination and drawn this. Okay. Scary. Okay, that is one problem. So definitely this is not looking like a sign. There's other very big problems here. What is this here? There's some kind of tail here, some kind of tail here. Real life we don't have this. No? The sinusoidal is just a continuous sinusoid. Ugly. Okay, what else? What are the other problems? What is this fish here? Why this fish? Okay, so there is another problem here. The problem is that this part has to look exactly like that part. Okay, if the figure is drawn properly. It's not looking like that part. Right? This is like a compressed version of that, right? You can see that. And then you of course have all these things. Okay, there is another problem here. So can you make out what this is? Line space. What is line space? What is line space? This is in a finally published textbook which students are using. Line space. So why this happened? Because the author drew this figure on paper and he wanted to indicate to the draftsman that okay, you leave a line space here. So he wrote line space. So the draftsman, line space in nice handwriting. Nice. So this is how it is. No, this is how some of our textbooks are, and this stays in their head. That is why the diode curve they draw it. So this is so easy to produce, right? You can do this with MATLAB, you can do this with Python, you can do this with some other package. So this is what it should look like. This sinusoid should look like a sinusoid. This is the modulating signal, and this envelope has to be exactly the same as that. And in fact, you should try to also draw it on the same scale so it looks exact. So this should stay in the student's mind and not this. Okay? You see the difference? Striking. There is no line space here also, right? Okay. So from the same book, we have another figure here. What is the problem? Anybody? Big problem in this figure. There is no emitter. So there has to be an arrow, right? When you show a transistor, there has to be an arrow. So the arrow is missing. And students are paying money to buy this book. It's in the market. Foreign author. Which foreign author? Generally foreign authors would not, the publishers would not allow this kind of nonsense in general. That would be rare. But in Indian scenario, just anything goes. The same thing is true also about our journals. You pay money and you can publish a paper. and no, without any review, nothing. And then that you can put in your resume. So that is how our whole system is working. Okay, so here is another how bad textbooks can hurt. Here is another example. What is it trying to show? So from the same book. What is it trying to show? Lagging phase angle, leading phase angle. Right? Okay, so many of these things are okay, but this is not okay. Right? This is not looking like a sinusoid. Okay, and if you talk about phases, the waveform has to be sinusoid. Right? Alright, so there are many issues, and I'm just going to illustrate how circuit simulation can help a little bit in at least making sure that students don't take away with them some wrong stuff in their heads. So it's very simulation in general is very useful, and this probably also applies in other engineering classes. Very useful for teachers to show realistic, accurate waveforms in class. You don't need to draw some. If your drawing is not good, or if you don't understand it very well, you don't need to bombard students with some wrong stuff. So it's very useful for teachers to show realistic, accurate waveforms in class. Teacher can work out a circuit problem and show simulation results to the students to reinforce their understanding. This really helps. For students, let's say you ask the students to work out something, right? They work it out, and now you show them some simulation results saying that okay, it is the same exactly what you got. They feel happy, right? It reinforces their learning. Students can be assigned homework problems and asked to check their solutions using simulation. This is also a possibility. What is the limitation? The only limitation is that students do not have access to to a laptop or a desktop when they are sitting in class, like you are sitting right now, right? So they don't normally bring their laptops. Some students may not even have laptops, but those who do don't really bring their laptops to class. And so that is the whole motivation of developing this app for teaching electronics. It's called Sequel app, and I'll show you some snapshots. Oh, in the meanwhile, I also conducted some survey in my own class. It's called E112 electronics class, and I asked two questions. One is simulation results. Are they effective in learning basic concepts in electronics? And so many people strongly agreed. So that is good. So the students, this is from students, and there are no obligation to say good things about the teacher. It's a totally anonymous survey. So they could say whatever they want. So most of them agreed that it is useful. Simulation helped me to understand the effect of circuit parameters on the operation of the circuit. Here again, many people said that it was useful. Right? So all this is just to sort of convince you that simulation can indeed be effectively used in a classroom setup. So that brings us to this Sequel app for active learning. It is an app which is already available in the Play Store, and some of you electrical engineering people can download it and look at it. Alright, so what is my idea of using this app in classroom? Okay, so let's just go through that. So what is the conventional teaching method? The teacher lectures, like I am lecturing right now. The students listen, they take notes, right? Okay, so the problem, this is more or less like a passive mode of classroom, right? Here the engagement on part of the student is low. The student is not actively involved. Okay, so that puts some limitations on the way the student learns. On the other hand, there is something called active learning, and this has been around for like the past 20 or 30 years in the literature, and there are a lot of papers on this in literature saying that this is very effective. And so what is active learning? In active learning, students play an active role in learning by participating in some activity which is related to the topic which is being taught. And apart from, so of course it's still listening to the instructor, but apart from that, the students also play an active role in the learning process. So there is an activity the activity could be as simple as solve a problem. Okay, so the student has to actually do it. And it is well established that active learning leads to enhanced understanding of the subject. There are a lot of studies in the literature which compared two classes, one which had active learning, one which had regular conventional learning, and they showed that the active learning class did much better. So in the context of electronics courses, active learning can take place through problem solving. You can cover a topic and say, okay, now solve this problem. Or you can simulate, you can ask the student to simulate a circuit or try it out in the lab. Now this try it out in the lab of course is not possible because the students are sitting in the classroom and you can't have all the equipment in the classroom. But simulation is definitely possible, and that is what will bring us to this SQL app. So in this talk we describe an app which is aimed at active learning in electronics and power electronics courses. How does it work? Okay. So this is like a sequence of the events that will happen. So first, the teacher states a problem related to the topic being discussed. For example, the teacher covers, those who are in electrical, say let's say you cover some Thevenin theorem, right, in class. Alright, so now you state a problem related to that particular topic. Okay. Then the teacher goes through the complete solution for the problem involving inputs from the students. So the teacher can work it out on the blackboard with of course some inputs from the students. Okay. Alright, so now the teacher says, alright, so you have understood this problem. Now let me ask you one question. That question is, how will the solution change if some resistance is changed from 1K to 2K, for example. Right? So this is the question that the teacher has asked now. After going through the entire solution. Okay, so all that is the problem has remained more or less the same, except some small change has happened. Right? So now what the students have understood this whole process. So the students will work out the solution to the new problem, this problem, on paper. Okay, so that is the next step. And now the final step is where the app comes into picture. Students verify their answer using SQL app. Okay, so everybody has mobiles these days, so they actually can simulate the circuit that is being discussed and check if whatever they worked out on paper is indeed what they are getting by simulation. Okay. So this is supposed to be the use of how the app is going to be used. So here is an example. Is an oscillator circuit. So the questions are, what is the find the oscillation frequency and sketch some waveforms at VC and VO. Right? Okay, so the teacher has stated this problem. Next step, teacher is going to work out the solution in class. Alright, so after the teacher works out the entire solution on board, he is going to show this simulation result from the desktop. Okay, and you can suppose the period is let's say the frequency is 1 kilohertz. From this, you can show the students that okay, the period is indeed whatever, right, or the frequency is indeed whatever you calculated. The teacher shows the simulation results, shows that the results are consistent with the results worked out in class. So this gives the students some confidence that okay, whatever we are learning is indeed it makes sense, right? Alright, so now the teacher says, alright, what will happen if I change some R1 from 27K to 15K, or I change this R from 5.6K to 10K, etc., or this zener voltage of the diode is reduced by 2 volts. What will happen? Okay, so students have gone through the solution of the previous problem. They should be able to tackle this fairly easily if they understood, right? Alright, so and that is where the app comes in. So now they have worked out the whole thing on paper, and now they are ready to verify with the app. So the app has got these variables which the students can change: the zener voltage of the diode, R1 value, R value, and so on. Okay, and then the student can apply these changes and then look at the waveforms. Okay, from the waveform, the student can make out whether whatever answer he has got on paper is correct or not correct. Alright, so I think that is all I have. It was a bit short, but I hope I conveyed the use of the app and also the simulation to you. Do you have any questions or comments or any thoughts that you want to share on teaching? Anyone? You can share your experiences in general, okay? Because everybody is a teacher, so you can Okay, so that's good. So you can actually encourage students to use these in, but it has to be design. Okay, so designing is not something that is very suitable for classroom teaching, right? I mean, it's a long activity. Not sure if you can actually use it in class, but you can certainly give problems based on that, design problems. But if you are giving homework problems, then students may as well use laptops or desktops. Okay, so this app is particularly useful in a classroom setting where they don't have desktops available. Yeah, but there will be other things in other branches of engineering as well. Any other branch has chemistry or anything? Chemistry, I have seen some app which shows the crystal structure and so on. So that kind of thing is useful. Any other comments? Anyone? So anyway, you can try to download this later. It's called SQL app. It's in the App Store. You can just go to App Store and type SQL app. It should show the app there. SQL app. Where is it? Or let me. I'll just show you the. And there are already lots of questions based on this app that the teachers can use, and they can all be found at this in this website here. You don't need to remember. Just if you just type SQL circuit simulation in Google, you will probably get this. And if anybody has any questions, you can always contact me. Alright, any other comments or questions? So, yeah.
As you had mentioned, problems that we often face and why the engineering education is not what we expect it to be. And in that, the first point was the low motivation level of the students. This is, in fact, I presume everybody experiences it.
Everybody experiences it, including in IITs.
Yeah.
Okay, let me
Why? In fact, a couple of years back, there was a discussion in IIT Delhi, and one of the professors in textile department said that if there is a class in the core subject, the attendance will be 30%, and if there is a class in finance, the attendance will be 90%. And the same thing I was once sharing in IIT Roorkee. The professor said it's even worse than that. He said even in finance class also it is 60 to 65%, not beyond that. So there is in general a kind of disinclination among students and across institutions. So how do we really manage that? And often we, just a minute, often we talk of remedial classes. We say when the students are not attending the regular classes, leave aside the remedial classes. So how do we really address this, and how the motivation level has to be increased?
Yeah, so I don't have a, so the only way the motivation will change is that there is a, package, good package waiting for them at the end of the core areas, right? That is how it will change. But I would say at least we should try to, all of us should try to make the classes as interesting as we can in the core areas. I mean, then they might come to the class just because they find it interesting, exciting. And that is what I was trying to say. There is burnt out business I have heard before, and it's just an excuse. Okay, I mean, how come I'm not burnt out? I mean, I also, all of us, right? We are still in academics, no? How come we are not burnt out? So that burning out business, I don't agree. But it is true that it is. I mean, this whole coaching class and preparation, etc., is rather intense. And very often, what happens is the student may actually have interest in some other area, but then everybody has to do engineering, so that student also. So all those societal factors are there. I'm not sure. I don't have a solution for that. Right? But this burning out business, I don't agree with. Okay. So that is an excuse, and the real reason is okay, there is maybe in the core area is he or she is not excited enough about core areas, or there is not good enough a good enough job, maybe something like that. Okay, that can. So if for example the same program is in finance, right? Whether he is burnt out or not, he will still attend all classes and do well, right? Like he said. So this burning out is an excuse. Any other classes? Yeah. So I end by requesting you all to make your classes interesting and exciting, no matter what you teach. Okay. Thank you.